Welcome to this explainer. Have you ever actually wondered what makes certain software run blindingly fast, just seamlessly pulling up the exact information you need, while other programs lag, freeze, or just completely crash right when you haven't saved your work? Well, the invisible magic behind that software speed isn't just about having a faster processor. It actually comes down to a really fundamental concept: data architecture. So today, we're going to demystify exactly how computational systems organize and process information under the hood.
Okay, let's dive into this. Here's our roadmap for today. First, we'll tackle the data architecture challenge. Second, linear sorting, specifically stacks and queues. Third, we'll look at complex patterns like trees and graphs. Fourth, measuring efficiency using big O notation. And finally, we'll wrap things up with the digital library quiz. Let's get started.
Section 1. The Data Architecture Challenge, Managing System Resources.
So, the core problem every developer faces is that data sets are just constantly expanding. It really is that simple. Fast, reliable software depends entirely on how that information is organized. I mean, if you just throw data into a system randomly, finding it again is like searching for a needle in a haystack. It requires massive amounts of system resources and slows everything down to a crawl. To truly understand this, we're going to look under the hood of software speed by taking some pretty abstract computational concepts and grounding them in everyday physical metaphors.
Section 2. Linear sorting, focusing on stacks and queues. To get a handle on these foundational structures, let's mentally step out of the digital world for a second and walk into a busy, bustling cafeteria. Let's start with a stack. Imagine a worker managing a tall stack of clean trays. When they wash a new tray, they place it right on top of the pile. And when the next hungry customer comes along, which one do they take? They take the one right off the top. The last tray placed on the stack is naturally the very first one taken off. In computational systems, this is called last in, first out, or LIFO. It's a linear data structure that is incredibly efficient when your system only needs to interact with the most recently added piece of info.
Now, what's really interesting about this slide is how we contrast that stack with another fundamental structure, the queue. Think about the actual line of people waiting to get their food in that same cafeteria. You definitely wouldn't want the last person who joined the line to be the first one served, right? That would be total chaos. Instead, the line operates strictly by the order of arrival. The first person in the line is the first person served. In data architecture, we call this first in, first out, or FIFO. So while a stack, like those trays, is last in, first out, a queue handles items strictly by their chronological order of arrival. Choosing between these two completely changes how your system processes information.
Section 3. Complex Patterns. Let's talk about trees and graphs.
Okay, we're moving out of the linear cafeteria line now and stepping into a vast digital library. Because, well, not all data can be organized in a straight line. Sometimes you need complex patterns. Think of trees as representing hierarchical patterns. A tree structure organizes information in a strict top-down flow. It's exactly like a library divided into wings, then aisles, then shelves, then specific books. It's a hierarchy. On the flip side, we have graphs. Graphs represent highly interconnected, networked data points. Instead of a top-down hierarchy, a graph maps out how everything relates to everything else. It's like a giant web of cross-references, showing how one single book might cite dozens of other authors across entirely different subjects. When data is interconnected like that, developers use graphs to navigate those complex relationships.
Section 4. Measuring efficiency with big O notation.
We've looked at how things are organized, but as a system grows, how do we actually know our architecture will hold up under pressure? Well, that brings us to big O notation. This is a critical metric used across the industry to evaluate how algorithm performance changes as datasets expand. So the crucial point is that big O is the ultimate tool for measuring the efficiency of your code as data naturally grows. You might write software that runs perfectly when managing 10 items in a stack, but big O tells you exactly what happens to your system's resources when that data set suddenly explodes to 10 million items. Let's look at this relationship in action. On the left side, we have input size increases. This is your data, rapidly expanding. On the right, the resulting time and space complexity. Time complexity is just how much longer the algorithm takes to run. Space complexity is how much more memory it eats up. Now watch what happens. As that input grows, big O tracks exactly how steep the cost becomes. If your code isn't efficient, time and space complexity skyrocket. They instantly drain your resources. They grind your fast software to an absolute halt. Big O is how developers predict and entirely prevent that disaster.
Section 5. The Digital Library Quiz. Time to test your knowledge.
All right, Here is your first question. Which data structure follows the rule of first in, first out? Think back to our bustling cafeteria. Are we talking about the stack of trays, or are we talking about the line of hungry customers?
The answer is the queue. Just like people waiting in line, a queue handles data strictly by its order of arrival, first in, first out. A huge congratulations to everyone who remembered the difference between the trays and the line.
Let's move on to our final, slightly more complex question to really lock in this overarching concept of algorithmic efficiency. What exactly does big O notation measure? Take a quick second to recall that two-column table we just looked at.
The answer? It measures time or space complexity as input size increases. And this brilliantly illustrates why picking the right data architecture makes or breaks your system's resources. Big O forces us to recognize that organizing data isn't just about making things look neat, it is about ensuring your software survives the inevitable growth of its own success.
So, we've covered the invisible magic behind fast software today. We went from the linear simplicity of stacks and queues to the complex networks of trees and graphs, and we saw how it's all graded by the harsh reality of Big O notation. The very next time you open a blazing fast app, I want you to remember the hidden structures holding it all together. Armed with this knowledge, how will you architect your next digital cafeteria?